Okay, so hello everyone. I'm very happy to host Yahav Bechavod that will talk about metric-free individual fairness in online learning. So, Yahav, the stage is yours.
Thank you, Elad. Thank you all for joining us. The title of the talk is Metric-Free Individual Fairness in Online Learning. The talk is based on joint work with my two colleagues, Christopher Jung from UPenn and Stephen Wu from Carnegie Mellon University, to appear in Europe's 2020. So, as we all know, machine learning algorithms are becoming more powerful than ever before, and they're altering the way the traditional way in which tasks are being performed. And as part of the change, algorithms are now intensively involved in decision-making mechanisms that crucially affect people's lives. Let's see a few examples. Predictive policing, hiring, in the criminal justice system, and in credit assessments. So these are just a few examples. In all of these examples and others, algorithms are now offering many benefits in terms of accuracy, in terms of efficiency, and also cost savings. However, we're seeing a lot of these reports as well about bias and unfairness. So this is a report about the criminal justice system. A beauty contest was apparently judged by AI, and the robots did not like dark skin too much. And this is a report from MIT about hiring, and from central banking about credit assessments. So in an attempt to better understand the problem of bias, in recent years, and I'm talking since 2011 or so, research in algorithmic fairness has emerged, and a big chunk of this research is aiming at providing algorithms that are highly performing, but with fairness guarantees. So the first natural question, right, the $1 million question is, what do we consider fair? This is a long-standing question, and is far beyond the scope of this talk. I'll just say that an overwhelming majority of the work that we've seen in algorithmic fairness literature is focusing on statistical group fairness definitions. And to give an example and then explain more about these definitions, let's consider a loan approvals example, on which on any given day, a bank deploys a loan policy. And then for incoming loan applicants, the bank wants to predict whether the individual is going to repay or default on payments. So this policy can look at features such as age, income, education, repayment history, but also features that we might deem as protected, right? Such as gender or race or others. So qualifying for statistical group fairness guarantee is a guarantee that holds on average on groups. So let's give a few examples. So the first is called statistical parity. And that means that if we look at the sensitive bit that is gender, we approve loans for the same fraction of male and female candidates. So let's say 80% of male candidates, 80% of female candidates are approved. The second guarantee, equal error rates, the same probability of a mistake regardless of gender in this case, or the other protected attribute. And we can look more closely at the types of errors. These are definitions 3 and 4, equals false positive rates or equal false negative rates, right? Because usually in these cases, one type of mistake is, we like to think of it as a mistake in favor of the individual, such as giving a loan to someone who might not be qualified. And the second type of mistake is generally against an individual. So if you deny an individual who's qualified of a loan, that's harmful. And we want to equalize for the type of the mistake. So regardless of the definition that we pick here, one thing that you observe for all of these is that these hold on average level, so not in an individual level. So all of these group fairness definitions are very easy to operationalize. So we can learn the very accurate predictor, the best accurate predictor under the condition that each of these hold, or we can select any one of these definitions. However, the guarantees that we have, as we've seen, are guarantees that hold on average, hold on a group level. And then these guarantees are very weak if you look at the individual level. So there are very weak guarantees for individuals. And what do I mean by that is, say that I want, let's give an example, say that I want to start a small business and I apply for a loan. And let's say that I am a green male. And let's say that this is the distribution of candidates. There are male, female candidates and green and blue candidates. And the ones that are accepted are the ones circled by red. So we can see that if we look at male versus female candidates, we have the same probability of being accepted. So let's say the criterion here for fairness is the acceptance rate. So right, if you look at the first column, we look at the second column, we have the same fraction of accepted candidates. And also if you look at the first row versus the second row, blue individuals versus green individuals are accepted at the same probability. But if we look at a combination of these two features, so green males are never accepted and blue females are never accepted. So say that I'm a green male, I could be the best, most qualified candidate, but I never get accepted. So I have zero probability of getting a loan, regardless of my qualifications. So this is an example of how group definitions do not hold as we go to a final level. In this case, a combination of features, or more specifically, individual levels. So we will see as we go to a final level. Right, so if I'm a green male, regardless of what I do, I get my loan application rejected. So the very guarantees for individuals that are given by group fairness definitions is, let's say that I was poorly treated by the algorithm. My only comfort is that there exists one of the two happen. So it's either that an individual from the other group is treated poorly as well, or an individual from my group was treated better than I was. So this is the only comfort. This is very dissatisfying from the point of view of the individual. Okay. Questions so far? Okay. So in an attempt to address to give better definitions that give guarantees for individuals, in 2011, Dwork et al. Introduced the notion of individual fairness. And this notion of individual fairness demands that similar individuals should be treated similarly. And what I mean by that, the mathematical definition is, given a soft predictor that we denote here by H, let's say this soft predictor is given the probability of X, the individual X given a loan. So the difference in predictions between any two individuals, X and X prime, is smaller or equal than the distance between these two individuals. And the distance is given according to some similarity metric between individuals. So this metric is essentially measuring how similar are loan applicants X and X prime. So we want that for similar candidates, the difference in predictions is small. So we want to treat similar people very similarly. And so ever since its introduction in 2011, it was largely not operationalizable, this notion of individual fairness, although giving a strong guarantee for individuals. And the main problem was that the similarity metric is often unavailable in many settings. So it's unclear where the metric can be found. And it's also unclear how can we learn this metric. So think of the credit assessment setting. It's not clear how to define who should be treated similarly, or which two individuals are similarly situated. And even when an individual, let's say a financial advisor, has a clear idea of which individuals should be treated similarly, humans generally have a hard time enunciating the exact mathematical formula. So let's say that this individual has a clear idea of who should be treated similarly, but then I ask the financial advisor to give the exact formula, and it's difficult. It's difficult to give the exact formula. And also, this individual might have this idea in mind, and then when asked who are similarly situated, he might report his idea, and then it might not be consistent with any metric. So the triangle inequality, for example, might not hold. So the first attempt is we ask an individual to give the exact formula that measures similarity for loan applicants. And for that, most humans will say that it's hard to tell the exact formula, even if it's in mind. So in order not to do that, a second attempt is to ask what is the exact distance. So we can ask numerical queries. Let's say I give two individuals, and I ask this financial advisor, what do you think is the distance between these two individuals, 5 and 17? And then report any distance between, let's say, a 0 and 100. But for humans, it's generally more difficult to give the exact distance, to give the exact number. It's easier to say whether these two individuals are very similar or very far apart. But to give the exact number and be consistent across multiple queries is more difficult. So what we do, the approach that we suggest in this paper, is we introduce a human auditor for fairness violations. And when I say violations, I mean we ask the auditor to spot a pair of similar individuals who are treated very differently by the algorithm. And then if the treatment was very different for individuals that are similarly situated in the eyes of the auditor, right, it's very easy. It's very easy to say, oh, this is a fairness violation. This is something that is not right. This is something that the algorithm did not get right. And this is based on the assertion that the auditor knows unfairness when he sees it. So he might not be able to give the mathematical formula, but he's able to say, this is where you have a bad decision. This is where you did something that is unfair. Okay, so I'll just state the contributions before I go into details. So first we introduced this human auditor feedback model based on fairness violations, not numerical queries. And it will be metric free. We remove these classical metric assumptions. And it will feature easy auditing, no numerical queries, only reporting fairness violations, and we will only require the auditor to report a single violation for each batch of individuals. Let's say 100 individuals show up on a given day. We will see that it's enough to require this fairness auditor to report a single pair in which there's a fairness violations in order to learn. And second of all, we introduce an online learning algorithm that is general. We'll have no assumptions on the hypothesis class. No parametric assumptions on the similarity function, and will also be efficient. Can be implemented efficiently if we have access to an optimization oracle, so an oracle for solving unconstrained ERM. And the guarantees that we give are for the adversarial arrival setting. So if loan applicants, for example, they arrive adversarially, not from a distribution, we give no regret for both accuracy and individual fairness. And for stochastic arrivals, if individuals arrive from a distribution, we give also generalization guarantees for accuracy and for individual fairness. Questions so far? Okay.
Yes. Can I ask?
Sure.
This is like a basic question. Sure. I'm trying to understand where does this bias come from? We have an algorithm that's optimized, to optimize the chances that the loan will be given back. So how do we know that this bias is not actually true? Let's say I find the bias by where someone lives. So maybe this is something the bank wants to know.
Yeah, so there's always this question of correlation versus causation. So whether we deem some feature as protected, or whether we think this feature should, in fact, affect the true probability of repayment, or we think this is an artifact of past discrimination. So I'll give you one example. Let's say that you want to predict who is more likely to steal a car nowadays in the US. So, right, the prediction, the probability in the African American community is higher, according to some studies that were conducted. But we do not believe that the probability or the likelihood of stealing a car should be encoded that it's somehow encoded in skin color, that skin color should affect this probability. We believe that this probability is affected because of past discrimination, right?
But isn't saying that kind of like rejecting the whole idea of learning from statistics?
How
like,
so?
The statistics are real. And now you're saying,
sure.
I don't like the results, so let's change them.
No, that's completely not, that's not what I'm saying.
If I would ask, I want a machine learning program asking where should I park my car if I don't want it to get stolen. Isn't that something I would want to know?
Sure.
Where do people live?
What I'm saying is that the notions of success is the notions that we choose to look at. And society as a whole, in certain settings, might look at notions of success that are broader than the ones that we are used to. Okay?
Right.
So we might look at short-term classification and accuracy, but we may look at different notions. We may want to look at more broader notions of success. And as I said, there are many settings in which optimizing only for the immediate accuracy is not what we select to do as a society. I'm not saying this is something that we don't want to do. I'm saying this is a societal question, right? In some cases, for example, we want to have the approach of affirmative action, right? I'm not saying this is wrong versus right. I'm saying these are selections that should be made on a societal level.
Okay, I can agree on that. But the question is then, where do you put the limits? Because it can become very political, this whole thing.
I think that in the fairness regime, you want to ask like the false positive should be similar in both groups, even though there is more statistical chances that in, I don't know, black neighborhoods, the car will be stolen, for example. You still don't want to have more false positive in those neighborhoods than in like white neighborhoods.
Yeah, so I agree. This is a societal question. It's also a trade-off between the things that you want to optimize over. So I don't have a definite answer for you, and of course I do not have a definite answer in every setting. But what I can tell you is that in different settings, the things that the measures for fairness that you might want to look at might be very different from one another. Okay? So
I think it also relates to the limitation of the model. Because maybe there are exceptions that the human will easily notice in the people that should get a loan, but because they have a cofactor that doesn't affect them as much, but they still have it in their features list. And the machine, the statistical algorithm won't notice it easily. I think actually answer the
I think you're talking about the auditor model on how likely is it to answer these questions that we asked?
Yeah, about what is discrimination or unfairness, like how?
Right, but yeah, but different people have different opinions. So even if you have this human auditor, you might have different auditors. They have different opinions, and this question of what should be considered fair, I think, has been around since the dawn of humanity, and this is far beyond the scope of this talk. But I think that it's good to say that this is a societal question that should be answered on the societal level. And our role as computer scientists, I feel, is to better understand and to give solutions and to give the best trade-offs that are possible. And then the final decisions are made on the level of the stakeholders. But we want to be able to give the best trade-offs and best algorithms that we can. Okay. So I'll start by going into details with the human auditor model. So first we need a couple of definitions. X is an instance space, Y is the label space, binary label space. H is the hypothesis class. We assume that H contains a constant hypothesis. We allow for convex combinations of hypotheses to be deployed. That means probability vectors over base hypothesis. For each prediction, we have the associated loss. This is the 0-1 loss. And we generalize the 0-1 loss to hold for convex combinations by looking at the expectation of the loss over the base hypothesis in the combination. Okay, so individual fairness. So first we assume that there's a distance function. This is not a metric. So this is a distance function. We do not necessarily demand it to be a metric. It does not have to obey the triangle inequality. But the only two requirements is that it's non-negative and symmetric. And next we define an alpha fairness violation to say, so for any policy pi, a convex combination of base hypotheses, we say that it has an alpha fairness violation on a pair X and X prime if the difference in predictions is larger than the distance between these two individuals plus some slack of alpha. Okay. And as we've seen, the auditor receives, let's say, n individuals, let's say 100 individuals with the predictions. And then you might say that there is a fairness violation if there exists one or more violations. Or if there are no violations, it returns null, or it returns there are no unfair treatments. This is the fairness feedback. And formally, we define the auditor to be a possibly stateful. So a possibly stateful auditor takes a reference set. These are n individuals and a policy pi, and it outputs either a pair of individuals if there exists a fairness violation on this pair by this policy, or if there's no violations, returns null. So if there exists multiple violations, we say that the auditor might return any violation arbitrarily. It might select any pair that it wants and report this pair with a fairness violation. And the setting that we're interested in is the online fair batch classification. So in this setting, it runs by time steps or by days. And on every time step, the bank deploys a policy. And then k individuals arrive, and they may arrive adversarially according to this history until this round. So there's no distributional assumption. And then they're predicted according to the deployed policy. And then the auditor reports if there is a fairness violation on this set of individuals. So the learner essentially has two types of feedback. He has the misclassification or the accuracy feedback of the predictions according to the true labels, and also the fairness feedback. And this runs in days. On every given day, k individuals show, and between days, the bank may change the deployed policy. Okay, so this is pseudocode. The learner deploys the policy. Individuals arrive. These are k individuals, the x hat and the y hat. And the environment, in this case, the auditor selects the pair if there is a fairness violation. And then two types of losses at the end of each round, the misclassification loss and the fairness loss. So the misclassification loss is just the sum of 0-1 loss over all of the arriving individuals. And the fairness loss is defined as the indicator function of whether or not there exists one or more fairness violations. So if the auditor reports one violation, we have loss of 1, but if there are no violations at all, we lose nothing. Okay, questions about the setting so far? Okay. Right, so a natural measure of success in this adversarial online setting is the notion of regret. And regret is measuring essentially how the algorithm did comparing to the best possible policy in hindsight. So the first term that we have here on the left is pi t, the policies is the policy that is deployed by the algorithm on time t. And the term on the right is pi star. And pi star is the optimal policy in the policy class. And we look at the difference and we sum over the differences on each of the days. And if this difference in total is smaller than the term on the right, we say that an algorithm has a regret guarantee that we denote by this thing on the right. Okay, so so the first question is, what should we compare to? So, right, we want the highest performing policy somehow that is also individually fair. So we select the baseline to be all policies in the simplex over H in what we denote by this triangle. And so all policies that are alpha fair, so meaning no alpha violations for all of the days. So the policies in this class that, let's say the alpha fair policies are policies that if they are deployed on the arriving, for the arriving individuals, they have no alpha violations for the individuals that showed up on day 1, on day 2, on day 3, on each day. And we want to compare our performance to the best, to the most accurate hypotheses from this class. So for the algorithm's fairness level, since the environment may report violations that are arbitrarily close to alpha, adversarially somehow, we'll allow an additional slack of epsilon. And for human sensitivity levels, I think we can think of alpha and epsilon as constants, right? So for the human sensitivity level of detecting fairness or looking at fairness issues. Okay, so, excuse me. So in the paper, we give an algorithm such that for any stream, what we denote by ZT is for any stream of individuals and for any violations reported by the auditor, may be reported adversarially in any arbitrary fashion, we give the following two guarantees. The regret, we give no regret, or we give sublinear regret in terms of classification error. And we also give a second guarantee that says that the number of rounds on which we have a fairness violation of magnitude alpha plus epsilon is also sublinear. So we give both these guarantees, and the way that we do it is we reduce the online fair batch classification setting to standard online learning or to standard adversarial online learning, and we do so by creating a fake stream of examples. So we have the stream of examples, stream of individuals that show up in the original algorithm, and we have this auditor feedback that reports a single pair or nothing at all. And according to the original stream and the auditor's feedback, we build a stream of examples, now without fairness, for the second setting, for the standard setting. And then we do this, so this reduction is regret preserving. I will not go into details, but the upshot is that we can upper bound both of these terms by the regret guarantee of any algorithm for the adversarial online learning, for the standard setting, by the regret guarantee. And then, so given any algorithm for the standard setting, it's an upper bound for both these terms. So the theorem, or one of the theorems that we give in the paper, is for one such algorithm. It's called context follow the perturbed leader. I will not go into detail about the separator set assumption. This is some assumption on the hypothesis class. That allows us to solve the problem efficiently. So using this algorithm, we achieve both these guarantees. We get the regret for misclassification is big O, is at most big O of root T times log H, size of the hypothesis class. And we get the same dependence for the number of unfairness, for the number of fairness violations of size alpha plus epsilon across the runs. Okay. So yeah, so this holds under this assumption of the separator set, but I should mention that we can also get these guarantees inefficiently if this does not hold using multiplicative weights or so. Okay, so how am I doing in terms of time? Okay. So far we've seen the adversarial arrival setting, in which individuals can arrive in any fashion and with any labels. And so the question is, what if at some point, let's say in the loan approval setting, we want to deploy the learned policy? We want, let's say the bank wants to deploy a policy for the next month or so. And realistically, we observe that individuals are not expected to arrive from in adversarial fashion somehow. That we expect them to rather show up according to some distribution. So in order to even talk about generalization, we will assume now the existence of a data distribution that is unknown. And we would wish to output a policy that gives generalization guaranteed for both accuracy and fairness. Okay, so we will see that for accuracy generalization, the argument will be relatively straightforward since we have full feedback. However, it's more challenging to argue about fairness generalization. And why is that? So the first reason is we have limited feedback. The auditor is only required to report a single violation. There might be multiple violations inside these K individuals on every day, but the auditor only gives us one. Also, in the worst case, the auditor's feedback may pertain only to the deployed policy. Right, so if the auditor says you deployed this policy, it has a fairness violations on these two individuals, this is no numerical query. So for all other policies that have not been deployed and treat these individuals more similarly, essentially we know nothing. We know nothing of whether or not the other policies have a fairness violation. So in the worst case, the feedback that we receive is only pertains to the deployed policy in terms of fairness. And the third point is adaptivity, right? So even in the stochastic setting, even if individuals arrive from a distribution, the auditors may still select to arbitrarily report any pair on any round. So as a result, we cannot really use a uniform convergence argument because we have this limited feedback over the hypothesis class. So instead, what we do in the paper is we consider the average policy over time, over the run of the algorithm. And we will rely on regret guarantees of the original or the algorithm that we've seen, or any algorithm in the standard online learning setting, to upper bound both the accuracy and fairness generalization error. Okay? This is a formal definition of the average policy. I will not go over it. Okay, so first, the accuracy generalization guarantee. We give a high probability guarantee over the average policy pi average. And the guarantee is that the expected loss is as the loss of the optimal policy plus 1 over the number of rounds times the regret of the original algorithm or the online learning algorithm, plus a term that looks like 1 over root T. Okay, and think of it as root T, so we get this, the optimal plus 1 over root T guarantee. This is for accuracy. The more interesting generalization guarantee is for fairness. So, to talk about generalization for fairness, first we define alpha beta fairness. We define it to be the following for any two positive parameters. We say that a policy pi is alpha beta fair. with regards to distribution D, if the probability over pairs of individuals of having the difference in predictions larger than the distance between these two individuals plus alpha. So if the probability of having an alpha violation, this is what we have on the left, is smaller than beta. So ideally, you want alpha and beta to be very small because beta is the likelihood of hitting a violation, and alpha is how large is the violation that we're hitting. So if we have only very small violations and we don't see these violations very often, then we can say we have a good generalization guarantee. Is that clear? Is that definition okay? Questions? Right, so the fairness generalization guarantee that we give in the paper, this is it's a lot to digest, so let me parse that. So if we assume, let's say that for any round that we deploy pi-t, the policy pi-t that is deployed is alpha beta t fair, okay? Then with high probability, the average policy is alpha plus some slack term, I will get to it later, beta star fair, where beta star is this term that depends on the regret of the original algorithm plus root t. And this term, this slack term, is some relaxation for the size of the violations that we consider. Right, we will see later that it's difficult to give a generalization guarantee for the original, for alpha violations. So we somehow have to relax it to slightly larger violations, and then we can get a better generalization guarantee. So the way that this is proven in the paper, I'll only give the sketch. First, we upper bound the probability of seeing these slightly larger fairness violations. And we do so by upper bounding using this term, the sum over beta t. Right, so what is this term? This term, for any round t, beta t is the probability of the deployed policy on this round to have an alpha fairness violation. So we want to use this understanding that if the regret guarantee is something, in order to get this regret guarantee, we cannot somehow deploy many unfair policies because then regret would be larger. And second of all, we upper bound this term, the sum of beta t's, using the regret guarantee of the algorithm. Okay, so let's start with upper bounding the probability of slightly larger fairness violations using the sum over these betas. And the first question is, why not bound the probability of an alpha violation, the original smaller violation size? Okay, so let's suppose that for any round pi t is alpha beta t fair. We can give the following guarantee. We can say that the average policy is alpha sum of the beta t's fair. So why is that? So first, consider all policies that are deployed along the run of the algorithm. And then in the worst case, right, all fairness violations are as large as possible. So of size 1, of magnitude 1, treating one individual as 1, treating the other one as 0 with the probability. And in the worst case, also violations do not cancel out. So violations could cancel out if we have different policies on different rounds that treat a pair of individuals in the opposite directions, right? And then on average, the treatment is fair. So if we look at the probability vector over the average policy. So in the worst case, we do not have these cancellations, and also every time that a policy does not have a violation, it might have something that is arbitrarily close to alpha, but is not a violation. So what we get is, if we look at the space of, if we look at the joint distribution of individuals, and we place these green areas are individuals on which the policy, let's say pi1 has violations, alpha fairness violations, and the same goes for pi2, pi3. So what we get is that in each area on which one or more policies has a violation, the average policy has a violation as well. So as we have more and more policies, essentially, if this beta t, right, we imagine that this beta t would later be, the sum of beta t would be larger than 1. So we will see later that we'll upper bound it by the regret guarantee, and this looks like root t or something. This gives a vacuous guarantee. So the guarantee is somehow that for alpha violations, the average policy might have a violation on all of the pairs. So everything is in green here. So the second attempt to tackle this problem is what we did is we relaxed the size of the fairness violation that we are considering. Before I go into the dilemma, are there any questions so far? Okay. The second attempt is we relax this fairness violation to be an alpha plus another term. And we select this Q over T and think of capital T is the number of days for which the algorithm runs. And Q is any integer. So for any integer, we get this the following guarantee. If you look at alpha plus Q over T, slightly larger the violations, we can say that the second term, the beta term, is 1 over Q times the sum of betas, right? And ideally, I mean, later we will pick, we'll see how we pick this Q to get the final statement. Right, so the proof sketch for the larger violations. So let's say that we consider this alpha plus Q over T violation. So the key observation is the following. So for any pair of individuals, X and X prime, if the average policy has such larger violation of alpha plus Q over T on this pair, then we know that during the run of the algorithm, at least Q policies, there exists at least Q indices for which the deployed policy has a violation of at least alpha. Okay? Because otherwise we would not be able to have the average policy having this larger violation. So we know that there exists this Q indices. And because of this first step, we know that the probability of the average policy having this larger violation on X and X prime is at most 1 over Q times the sum of betas. So it will be helpful to look at this illustration. So the green areas, the individuals on which the average policy has a violation size of alpha plus Q over T are only areas on which there exist at least Q policies, original policies, that have a fairness violation. Okay. Questions about this sketch? Okay. So once we have this lemma, we next link the sum of betas and the regret term, right? So now we bounded it using, we bounded the probability of observing violations by the sum of betas, and we want to bound the second term here by the regret guarantee. And for that, we prove the following, that with high probability, the sum of betas, or the sum of these probabilities, is at most the regret guarantee plus root t, or plus root t times log 1 over delta. Okay, so we arrive at the final generalization statement. So using this specific algorithm, context for the perturbed leader, but we can use multiplicative weights to get the same rates. We use this algorithm for efficiency. We get that with high probability, the average policy has the following guarantees. First, for accuracy, we've seen that it gets the accuracy of the optimal policy plus a term that looks like 1 over root t, or with dependence on log h. And this dependence on log h comes since we reduce it to the adversarial setting. Right, in the adversarial setting, we have this log h dependence. And second of all, for fairness, the average policy by the construction that we've shown has the guarantee of alpha plus lambda, and the beta term is lambda fair, where this lambda behaves like O of t to the minus 1/4. So think of t as being large, let's say 10,000, and then we get that as t grows larger, the size of the violation that we look at goes to alpha. We look at violations that are closer, arbitrarily closer to the original violation size, and the probability of hitting such violation also it goes to 0. With a rate of proportional to the number of rounds to the power of minus 1/4. Okay, so let's
just, ask me to tell you when there's
15.
minutes left.
Thanks. Okay, so let's recap. So first we started with introducing the human auditor model for fairness violations. And then in the context of online fair batch classification, we utilize this model where individuals arrive adversarially every day and require the auditor to only report a single violation. Next, we use the reduction by creating the fake stream of individuals for the standard online batch classification setting. So now without fairness, with no need for auditor. And we upper bounded the regret and the number of fairness violations by the regret guarantee for any no regret algorithm for this standard setting. Okay, this is here. And once we had these guarantees, we further, in order to look at generalization, remove the adversarial assumption. So if these individuals rather show up from a distribution, we were able to say, using a composition argument that we've seen for the average policy, and using upper bounds using regret, we were able to say that the average policy is with high probability accurate and is also fair with the guarantees in the former slide. Okay? Any questions? Right, so to recap, say I apply for a loan, so what am I guaranteed? So by any group fairness definition that is averaging over groups, I'm guaranteed that a group that contains me is treated similarly to another group. But there could be a lot of variance within the treatments inside the group. So inside my group, some people are treated poorly and some people are treated better, but group fairness notions don't really get it. So alternatively, the individual fairness guarantee that we've discussed, all individuals who are similar to me are treated similar to the way that I'm treated, approximately similar to the way that I'm treated. And from the point of view of the individual, this is a much stronger guarantee. So let's compare with some prior work on individual fairness. So we've seen the first paper by Cynthia Edwark et al. Made the conceptual introduction of the individual fairness notion, but they relied on the availability of the similarity metric. And this was, for many years, the assumption that made individual fairness not very practical. And in the paper by Rothblum and Yona from ICML, in 2018, they discussed the batch setting and they assume that there is perfect access to the metric. The metric is given, and for two individuals, you have the exact reading. You can see what is the distance, what is the difference between these two individuals as a numerical query. And they provided generalization results for the PAC setting. So in our setting, we don't even ask numerical queries. We ask only for fairness violations, and we do not need the measurements over all individuals, only for one pair in each batch of individuals that arrive. And this is sufficient for us to give generalization. Ilvento paper tries to directly learn the metric with numerical queries. We discussed that. And the Gillen paper from NURIPS, so they assume they have a different approach. They assume the specific structure for the metric and also discuss the linear bandit setting. And they have a requirement that the auditor must report all violations. Okay, so I'll conclude. So we've seen the statistical fairness notions. They give very weak guarantees on the level of the individual. Individual fairness was not operationalizable for many years due to the lack of metrics. And what we do in this work, we suggest a new approach based on a human auditor that reports fairness violations. We've seen how this is easy to implement. It's also metric free. Those violations that are reported by this by the auditor should not are not required to be consistent with any metric, and this might actually happen in practice. So you ask the individual to give you the measurements, the fairness violations, and it might not be consistent across different rounds with any metric. And we give an algorithm that is general with no parametric assumptions and is also efficient given access to an optimization oracle for unconstrained ERM. And we've seen in the adversarial arrivals no regret guarantees for both accuracy and fairness. And if we also assume a distribution from which individuals arrive, we give generalization guarantees for the average policy. And I'll conclude by saying that research in algorithmic fairness needs more what I call actionable notions of algorithmic fairness. And when I say actionable, I mean notions that give strong guarantees for individuals and that can be implemented efficiently. Thank you. This is all. If you have any questions, I'll be happy to answer them.
Hi. Question. Do the auditors get any instructions about violations, or it's just like their own, is it like predefined something? Or can we experiment with this? I'll give like a bad example I would expect wouldn't work. Let's say we want to predict, I know, basketball players, how good they will be.
Right.
And the auditors decide that we want it to be fair without regarding the height of the player.
Yeah.
Probably will not give us.
Yeah, so this is this is always the question of whether, let's say, age or height. In some settings, it makes sense, or they might be deemed as protected attributes, right? But in some other cases, that's more of a debate, or whether they should be considered, they should not be considered. Let's say age for applying for a specific job. Should it be relevant in some cases? I mean, so you can give the auditor instructions, but we want to think of the auditor as being more general and reflecting.
No, I'm asking more as the, sorry.
Sure.
I'm asking like in the regret guarantees.
Okay.
Like, can this always work? It sounds very impressive, but it's very surprising in my eyes. How can we bound the regret guarantees if we have no limit to this fairness? It just sounds like Incredible. It doesn't sound.
You mean limits in terms of what is the structure of the fairness violations?
Yeah, if
So
the auditor can decide any fairness, which can also be something completely like unrealistic, then how can we bound the regret?
So we have two requirements. We have this symmetric and non-negative requirement, right? But other than that, the auditor may report any violation. There's no, as we've seen, there are no parametric assumptions on how this metric should look like. This is not even a metric. How this similarity function should look like. And yes, in some sense, it's a bit surprising. It's more surprising in the generalization case where even though the auditor may report any violation, does not have, there's no distributional assumption somehow on the auditor, no probabilistic assumption, and any violation, but we're still able to say something about the generalization.
Okay.
Any other questions, anyone? Well, there was actually one over chat, and we do have a few minutes, so I'll go ahead and ask it. Netta Kenneth asks, the reason that we had bias in the first place is that human experts were biased, so won't the system that relies on auditors be,
Yes, this is a great question. Yeah, I think we should be very cautious, and we should be well aware of that. And when deciding who should audit or how should we handle this auditing process, right? So there could be a problem if the auditor suffers has these superstitions or has these wants to somehow has these views against a certain population, and yes, this is a real problem. So we were thinking about, in practice, this could be addressed somehow by maybe not having a single auditor, but by having more than one auditor and somehow aggregating. We did not explore it, but we thought it might be a good avenue for future work. And also, yes, this is, we have to be very cautious the way that we pick the auditor, the same way as we have to be very cautious with selecting any definition of fairness, right? So any definition that we commit to is also a societal decision and reflects some trade-offs that we as a society choose to make. And in these trade-offs, I can imagine some benefits and some harms, but it's always, we have to pick where to put the, where to put this knob, or where to, what definition do we commit to? So yes, I guess there is no full, complete answer to this question, other than we have to be very well aware of that and very cautious.
Okay, great. Thank you, Yahav. Anybody else have any questions? If not, which I think we don't, I guess everybody, you can unmute yourself, and let's thank Yahav for this great lecture today.
Thank you very much.
Thanks, guys.
Thank you.
Great, see you next week, you guys.